Okay, I think we can start now. Well, first of all, thank you all for being here. And thank you, Martin, for being here. It's such a pleasure to having you here. I will say some formal things and then I will say some other things as well. And so the formal things before we start, well, currently, Martin Everett serves as a co-director of the Mitchell Center for Analysis. Martin Everett holds a bachelor in mathematics from, I don't know how to pronounce that. Loughborough.
Very English spelling of the word.
Loughborough University, and a master in mathematics from Oxford University. At Oxford, Martin completed a DPhil, now I know what is that, jointly award by the Department of Mathematics and Sociology. So he has his dual sociology mathematical soul. And in 2009, he joined the University of Manchester after having worked at the University of East London, Westminster, and Greenwich. Martin co-founded the Mitchell Center for Network Analysis, which evolved from the existing Manchester Social Networks Group. The center is named after Clyde Mitchell, a founding figure in the discipline, who was a professor at Manchester and also Martin's sociology supervisor at the DPhil at Oxford. He is a past president of the International Network for Social Network Analysis, INSNA, and a recipient of the Siemens Award, the highest honor given by the organization in 2004. In 2004, he was elected as an academic of the Academy of Social Sciences, and Martin is a co-author of the UCINET software package, the most widely used software for analytical social network data. And Martin has consulted extensively on the use of networks with government agencies across public and private companies. So, to me, well, it's an honor to have you, Martin. We have the chance to be at Manchester together. So, having you here is quite interesting because now I can show you around that we are trying to do a community, and I'm very proud that you are here with us.
Well, first of all, thank you very much. Actually, I'd like to thank all Chilean people for the fantastic reception that we've received wherever we've been. But so far, we've only been in Santiago. I'm here with my wife. She was so excited to come to Chile that all our expectations so far have been met about what a wonderful country that you have here. So we really are enjoying, but not just the hospitality, but the beauty that's in your country. And for me, I'm a person who loves wine. What better countries to come to? Okay, right. What I want to do today is really talk about some of the work that I've been doing with my collaborator, Steve Borgassi, who I know is zoomed in to make sure that I'm keeping on track. I will present when there's difficult questions, Steve will answer those, okay? But collaborating was interesting because I was in the session this afternoon about collaboration. So it's really good to start off by saying that all of the work I'm presenting here has been collaborative. Some of the work is from other people. I just wanted to try and bring it all together in one framework. Well, now, yes. Okay, a little, you've already heard me. That's how you spell Loughborough for the pronunciation. As you can see, it's not obvious how to pronounce it. There are lots of words like that in English. We do it just to make it complicated. Here you see when I was young. So I used to not have hair. That's happened again. But in the interim, there was a time, that was me in Oxford. So when I was a student there, when I most certainly did have hair. Right, let's get on with the main topic. Centrality. Something, if you study social networks, it's one of the first things you'll find out about. You'll see a lot of writing about it. Often just said, it's the structural measure of importance in a network. There are many, many measures of centrality. There's often, well, new ones appear daily. I was editor for a long time for the journal Social Networks, and every week we would get a new centrality measure. I'm now the coordinating editor of Network Science, and again, quite regularly we get people that come in with a new centrality measure. Usually, to say often, actually nearly always, they are not new measures, but reformulations of measures that people have come up with before. They're often very poorly justified. The standard way they justify their new measure is they say, here is a network. They show one network or maybe a few networks and say, none of the standard measures, by which they just mean 4 out of the whole number, capture which we think is the most important, and our measure does. And to me, that is a very, very poorly justified use of centrality. So I really want to try and get across to you a context of how we should really be looking at centrality measures. I did a quick run of Google Scholar a week or so ago to find out how many papers had the word centrality just in the title, not even a keyword, just in the title. And the answer was there were 16,000 papers. So that gives you some idea of the popularity of centrality here. Some people try to get a handle on this by taking a very axiomatic approach. What makes a good centrality measure? The first was probably done by Sabidusi. That was done way back in 1966. He came up with 5 reasonably looking axioms, and only his centrality measure that he proposed worked on all 5, so no bias there. More recently, just as there's been many in between, I've just picked out a few. Baldi and Vigna in 2014 gave 3 axioms, and only a closeness type measure satisfied their 3 axioms. So commonly used measures such as betweenness and eigenvector did not satisfy their atoms. And more recently, Bloch, Jackson, and Tibaldi, economists, Jackson, a well-known network economist, actually suggest some axioms which, instead of trying to say the centrality measures should actually all fit these axioms, but try and use it to classify the centrality measures. I'm not going to go through what those are. What I want to talk about in terms of that kind of axiomatic approach are 3 very useful concepts that I think most people agree are okay. And the first one that nearly everybody says is right, that structurally indistinguishable nodes have equal centrality. What do I mean by structurally indistinguishable nodes? What I mean is, if I removed all the labels off this network and then asked you to tell me where number 8 was, you'd have only 2 choices. It was either here or here. Because 8 and 9, unless I knew where 7, if I knew one was 9, I would know the other one was 8, but it could be the other way around. So in other words, every structural property about that network, 8 and 9 would get the same score. So therefore, if we want centrality to be a structural measure, it should get the same score. For anybody mathematically, these are isomorphic nodes. Usually, we always say the maximum centrality score should be at the center of the star. Yeah. If I've got a star, there should be no way that somebody with the same number of nodes could get a higher score than the center. That those 2 ideas are more or less universally accepted, and they're very simple. There's one more idea which I think is a very useful way of looking at centrality. This was not done by Steve and me. This was done by my good friend Ulrich and David, Ulrich Brandes and David Schorch, who are at ETH, so Alejandro knows them very well. And it's a bit more complicated. They look at something which they call neighbor preserving. So they define this in the following way, and I'm going to give you an easy example to explain what's going on. First of all, the neighborhood of a node is all the nodes you're connected to. That's known as the open neighborhood. I can also have the closed neighborhood, which is all the nodes you're connected to you and you. So that's the difference between those two. When we say that node U is said to dominate a node V if the neighborhood here, the closed neighborhood, contains the open neighborhood of V. The centrality measure is neighborhood preserving if wherever node U dominates node V, the centrality of U is bigger than V. Okay, so you can check every centrality measure, is this true? And the answer is nearly every centrality measure satisfies this property. It's amazing how many do. And so it's a very useful property. We just make sure we understand this node thing. Yeah, so the open neighborhood of V are the squares. Yes, who is V connected to? It's connected to 4, it's connected to U, it's connected to 3. So the square nodes are the open neighborhood. The closed of V, the closed neighborhood of U, yeah, those are colored blue. So that's everyone U is connected to, including itself. So if it's neighborhood preserving, then basically what that's going to say is that the so that the U is dominating B, yeah, because we can see that in essence all of the square nodes are blue, and that's one way of thinking about that. What happens if you're in the domination position, that always means that since U is dominating B, every centrality measure, more or less, that's been invented, is such that U is more central than V. Now, we can think of times when perhaps this is not the case, because this has a basic assumption in there. And it assumes being connected to the better connected is an advantage. That's really the idea we're trying to capture structurally from what's going on here. Centrality measures, when this is not true, do not preserve this dominance. So I said nearly all measures follow this, but some don't. And the ones that don't, that we think are useful, you could invent pretend ones that are useless. The ones that are useful tend not to obey this rule at the top. And nor do they necessarily have the highest score at the center of a star as well, although often they do, but sometimes they don't. So where would this be useful? Well, this would be useful in a disease network. Yes, I don't really want to be connected to people that are well connected in an HIV network. Yes, this is not going to be very good for me. And most people would actually say, I want a measure that captures that. Or in a dislike network, yes? If I'm looking at who doesn't like me, I really don't want to be the most disliked person and think that makes me very central. It actually makes me very uncentral. So measures that pick those up do not successfully, do not obey this dominance rule. Okay? What's very interesting is we can design networks for which the dominance is always there. So one node always dominates another node. Some networks there is no dominance. And if one node dominates every other nodes in every pair of nodes in the network, then it doesn't matter what centrality measure you use. If it obeys that rule, then we know what the order of the centralities are. So when people come up with a new method, often they've just got different scores. It obeys this rule, but the scores are irrelevant because usually it's the rank order that I'm interested in. Who are the most central people? Who are the least central people? Not what their actual scores are. What this tells us, all of this tells us that data and context matter. I think that's the most important message. And that's the one I want to emphasize as I go through the rest of this. I'm also trying to make sure I time myself, seeing where I'm meant to get to. Excuse me for doing that. So, what can we do to help get a handle on centrality that's beyond those three simple concepts we've got there? Well, I'm going to suggest that we're going to look at three perspectives for looking at centrality. The first two are work that Steve and I have worked on over the years. The third one is entirely Steve's, so I want to give him credit now, in case he tells me off afterwards. Then I also want to look at, on the perspectives, is things about data that are very important when we start considering centrality. Whether my data is directed or not, whether it's all in one piece or in various different bits, whether it's disconnected. Do I have valued data? Do I have negative ties in my data? Or do I have two-mode data? All these important issues I have to consider when I'm thinking about what centrality method I'm actually going to use. Let's start with the oldest. This is a relatively old paper that Steve and I did about the walk structure perspective. I'm going to say in terms of a connected, undirected binary networks. Let's start simple. We will talk about the other data when we get further on, but just for now. So all nodes are connected via walks in that case. Yes, that's what we mean by a connected network. Yeah, if we recall, a walk is any sequence of adjacent nodes. Okay, and we can classify walks by various properties they have. Yeah, we have walks, which is any sequence in any order you like. We have things called trails, where I say, please don't use the same edge twice. We have paths, where I say, please don't use the same node twice. And finally, we have geodesics, which is take the path of shortest route. So those are essence of 4 different kinds of walks. And when we're looking at these centralities, we're usually looking at the properties of those walks. We may look at how long they are, or we might count how many of them there are. And there's various other properties I can look at these walks. Yeah. And the other thing, the centrality I measure of a node. There are 2 very different ways that types that I have here. Nodes can either be at the ends of the walk. Yes, so it's either the starting node or the finishing node, depending. This is undirected, so that really doesn't matter which way around. Or they can be nodes that are in the interior. Does the walk pass through the node as opposed to the walk start with the node or finish with the node? If it's the ends, I call it a radial method. Yeah. And if the node is in the middle, I call it a medial method. So here we've got quite a few things going on. We've got different types of walks, depending whether they're paths, length, paths, trails, geodesics, etc. We look at different properties of those walks. We look at whether nodes are in those walks. And what I can do is just to remind you again, the difference between the walks, the trails, the paths. A walk is something like 1U, 4U, 3, and you see I've used the 4U edge twice, so that's just a walk, it's not a trail. A trail would be 1U, 4, what am I going to VU, 3, right? That's every edge is, no edge is used twice, but I went through U twice, so it's not a path. A path would be 1U, V3, so that only uses this once, but that's not the geodesic, because the quickest way from 1 to 3 is go 1U3. But those are the very different types of walks that we have. So, for example, yes, degree centrality, which we know always, it's a radial measure because we count things at the beginning. We count the number of paths of length 1, in other words, who you're connected to. So I think of that as a path of length 1. Closeness, another radial measure. We sum the length of all the geodesics, so now I'm using geodesics, and my measure is the sum of the lengths from a node to every other node. Okay. Whereas between this is a medial measure. Again, this time I use geodesics. My count is the number of times it's in the middle of a path. So this is, because it's the middle of a path, it's a medial measure. Geodesics is my path. What I'm actually doing is counting those paths. And we can, for these, start looking at some of the measures that are in existence. I've just put a few of them on this little table. So what I've done is I've said, are they geodesics? Are they paths? Are they trails? Are they walks? So that's what goes across the top. Then what am I actually measuring? Am I measuring the length or the frequency? Or this one really is a combination of length and frequency. And what we can see in here, there's various ones of these have got things in. What's even more interesting is that various of them are empty. So even given these 16,000 papers, some of these are still empty. So if you want a research project, maybe it's to think of a measure. Good luck with getting it published, because as an editor of a journal, you've got to have a very good reason to publish a centrality measure. Okay, I'm not going to go through what any of these actually are in detail. That's for the radial measures, yes, where we start or finish at the node whose centrality I'm measuring. And we can do the same for the medial measures. Again, geodesics, paths, trails, and walks. Length, frequency, and length and frequency. A bit more sparsely populated, because these medial measures, basically, we notice the word between this nearly always occurs, because that's the word people have always used. Get the idea that it's somewhere in the middle. Right, so that's one way of I'm going to come back to this a bit later. That's one way of classifying my various centrality measures. And an important thing, as we will see later, is to think about those properties and how those relate to what it is you really want to measure. Let's look at perspective number 2. It's called the induced perspective. In the induced perspective, what we want to do is to see what contribution a node makes to a whole graph measure. What do I mean by a whole graph measure? I mean a measure that takes the whole graph and summarizes it with a single number. Okay? So, an example of a whole graph measure is density. We all know what density is. That's a whole graph measure. In fact, we call those whole graph measures, they're called graph invariants in the mathematical literature. Okay? So, we want to find out a particular graph measure that we think is important in some way. It's important because of my data or because of what I want to know about the network. Then what we do is we calculate that whole graph measure on the network. Then we delete the node whose centrality I'm interested in. And we calculate again the whole graph measure. And the difference between the two is the contribution that node has made to that measure. Yeah. The classic first example of this is something called flow between this, which I will briefly explain. If you don't follow it, it will not matter. Okay. So here's flow between this. Flow between this was an idea to try and generalize between this to valued networks. Okay, those values tend to be integer, but they need to be integer values. But computation is a lot easier if they are. So really, we imagine the network is a collection of pipes, and each pipe can take 1 unit of material. Yeah. The maximum flow is the maximum that can get from one node to another. And the total flow is if I work out the maximum flow between every pair of vertices. Okay, so this is the same example I had before, but let's see how we can see the flow. So if I wanted to get the flow from U to V, then I can get 1 unit directly on the adjacent path. I can get 1 unit by a 4. I can get 1 unit by a 3. So the flow from U to V is 3, maximum flow. If I look from 3 to 4, then it's only 2. There's different ways I could do it, but there's only 2. 3 to U to 4, 3 to V to 4. Actually, there's not different ways I can do it. But sometimes they can. If I want to get anything from 2 to anyone, it's got to be 1, because I can only get from 2 to the next one is 1, and there's no other way through it. Yeah. This is a very well-researched area in mathematics due to transportation networks. It's about kind of transportation networks. So I work out the total flow. I've got both of this network. Then I delete a node, and I work out the total flow. And the flow between this is the difference in those two values. Okay, let's look at some of the other measures. Degree is an induced measure. Yeah. If the graph invariant equals the number of edges in the graph, yeah. So if the graph is number, then it follows that deleting a node deletes the number of edges the node is adjacent to. Therefore, the difference in the two will be the degree. Yeah. So I can think of degree as an induced measure. First of all, not all centrality measures can be thought of in this way. Why is that? Well, why is that? It's because of this very neat little example. we look at the network here and the two nodes A and B. If I delete node B, yeah, then I get this network. If I delete node A, then I get this network. Yeah, we can see that. But this network is the same as this network. It's just a pair of vertices, a triangle with two people coming off the triangle. Yeah. So basically, if I use my induced centrality approach, it must be that the centrality of A will always be the same as the centrality of B. So I run this through UCINet. This really used to be the world's most popular software before R really got a grip. And this has actually run a degree, a collection of different centrality measures. And if we look, do A and B get the same score? What degree they do? Because it's an induced measure, so it must do. This one they do, this one they do. This is closeness, and there's a different score. Yeah, and this is average reciprocal distance, and there's a different score. But between this, eigenvector would be the same. Yeah. So the fact these are different scores tells me that closeness cannot be an induced centrality measure. So I cannot invent some graph invariant, some measure of the whole network that would produce closeness. So what graph invariants are useful? The nice thing about this centrality idea is that I'm not tying it as strongly to previous ideas. I'm not worrying about things like counting this or what kind of things is this. You can actually invent your own invariant that suits your own research agenda. But it needs to be defined for disconnected graphs, as we've just seen. Because I'm going to delete a node, and the chances are there'll be nodes in there that the graph will fall apart. So diameter, for example, is not a good measure. It needs to change under different node deletions. Yes, it's got to be a graph invariant that makes quite a lot of difference when I delete different nodes. For example, if I counted the number of nodes, then everybody would end up with the same centrality score, because you've just got one less node every time. So everybody would get the same score. So that would be it's a graph invariant, but it would be useless. Everybody would be as equally central as everybody else in every network. This, yeah, but like this, you should be able to find ones that are appropriate for your own research context. So this allows you to invent a centrality measure without publishing it, in one sense, because you say, I'm using this method, and I'm using this invariant, that satisfies what you actually want to do, rather than arbitrarily selecting some off-the-shelf centrality measure and saying this is appropriate for my context, because usually they're not. Okay, so they're many value processes and can be highly focused, so better than the off-the-shelf measures, I would say, because of that reason. One other neat thing you can do with it, which I just want to mention, is what we said is we have a graph invariant. Yeah, so the graph invariant, remember, is any measure of the whole network. But I can kind of double up on this, and I can use centrality itself as the graph invariant by adding up the centrality scores of every node in the network. Yeah, so the sum of every node centrality is a graph invariant. So I can create an induced measure of an existing centrality measure. That may sound a bit of an odd thing to do. We call this the total centrality. For each node, the difference between the total centrality and its actual centrality is called the indirect centrality. What the indirect centrality actually is, it's how much centrality does a node give to the nodes, to other nodes in the network. Yeah. So for degree centrality, actually, it's the same. It's the same as the degree. This doesn't give you anything. Why is that? That's because for degree centrality, if I delete a node, then I delete one off the degree of the individual and one off the person they're connected to. So that's not going to make any difference. Let me just give you an example where it does. This is the cap for mining data. Doesn't matter. This is a network. Okay, that's all we need to know. And I'm going to run between this on this network. So I run the between this on network, standard between the centrality. I calculate the centrality of every individual in the network. Okay, and I add those all up. Okay, that's my graph invariant. Then I delete a node, delete Godfrey. I calculate the between the centrality of every node in the network. I add them all up and I calculate the difference between Godfrey's actual between the centrality and the centrality, which is the difference between those two things. If I do that, I get this. So this is the between the centrality we've got here. Yeah. So this is how central everybody is in between this. But this, the indirect, is how much centrality does each node give to other nodes in the network. So we see, for example, Damien has got a between the centrality of 14, but by nature of their position, they give 38 points, 38 between this points to other people in the network. So making Damien really quite important in terms of not just their own centrality, but everybody else's centrality. What's even more interesting is people like Godfrey underneath, who has 13, but manages to destroy 9 between the scores for the other people in the network. So this person is kind of between the sink, taking centrality away from other individuals. So this may be useful to help to understand various things in networks, depending on the research context you've actually got. Fine. So, other notes here, we can use this on the edges as well as the nodes. Yeah, I can have edge centrality. I can do the same thing, exactly the same technique. I can have some graphing variant which is about the edges instead of about the nodes. Therefore, I can then delete an edge, recalculate it, and this gives me a whole collection. I can also use it for groups of nodes. Yeah. Instead of deleting one node, I delete 5 nodes. I delete, I don't know, all the people over 65. That's probably not a very nice thing to do. That's me, so that's okay. But and the other thing we could do with this is we could optimize the thing to find groups that optimize the induced centrality scores. And that's sometimes called the key player problem. And Steve has written a separate paper on that, although we introduced that idea in the paper where we discussed this. Okay, so that's my second perspective, the induced perspective. So we've got the kind of wolf perspective, induced perspective, and I now come on to my third, and this, again, all credit to Steve. This is his work. You read people when they justify a centrality measure, they often justify it in terms of flow. They say, particularly between us. Yes? It's about controlling the flow of information going through the network. Yeah, I'm in a position, Ron Burt's, all of Ron Burt's stuff is all about this people being in a position where they can control the people they're connected to relative to where they are in the network. So this flow is what? It could be information, money, gossip, disease, etc. All kinds of things. A lot of what we do in networks, we think there is something flowing through the network. That's why we think it's important. But different things flow in different ways, and they flow on different types of path. Yes, not everything flows the same. Emails, for example. Yeah, this is a lot ago we wrote this. We talked about emails. Nobody talks about emails anymore. WhatsApp messaging. Emails are duplicated and usually follow paths. Yeah, like I send an email to 6 people. It could be the same email. Yeah, so there's 6 duplicates, and they say, "Oh, that's interesting." They send it on to somebody else. They try not to send it to somebody they can see that's already received it. Not always true, of course. We often get sorry for cross-posting, but you know that's the basic idea. That's the kind of flow we'd expect emails to do. But look at the difference in the flow of I don't know, a coin going through a network. Yes, coins don't get duplicated. Well, I don't duplicate coins. There are people that do that, but it's not legal. The physical kind is not duplicated and can follow a walk. You know, I can bribe Alejandro and he could bribe somebody else and they could then bribe me. I could bribe Alejandro again with the same coin. Yeah, so it could follow a walk. So we can see that's just 2 examples. And Steve's come up with this really good, I'm not going to go through all these. You'll be glad to get this. Come up with this very clever collection of different duplications, whether it stays single or it comes in multiple copies. Yeah, so that's this column here, but it's duplicated. What does it do? Does it follow a trail, a path, a walk, a geodesic? Yeah, all those going back to that graph theoretic perspective, the walk perspective we had. And it's given them various names here. And these are kind of a brief description. I'm going to give you a reference to a paper that has all this material in. So you can look at this at your leisure in that or Steve's original paper as well. Then he goes on to do something else. Yes, he runs a simulation. It's basically an agent-based model. Seems like a good idea. And he uses the travel example that was down the bottom there. He calls it actually the package regime. So basically things follow geodesics. Yes, if you're traveling somewhere, you tend to want to go by the shortest path. Airlines seem to try and stop you doing that, but generally speaking, you try and go by the shortest path, and you don't go to two places at the same time because there's only one of you. So there's no duplication. He runs a simulation on a particular network and works out the average time to reach a selected node. So this is the way he's going to count what's happening in the thing we had before, you know, whether we had length and frequency and things like this. But yeah, and this turns out to be basically closeness. It's actually closeness divided by n-1, but it's closeness. You'd expect it because your shortest path to everywhere else. Yeah, that's great. Secondly, right, that's the first run. Secondly, runs a run for each pair of nodes, run simulation in which, if there are multiple shortest paths, one selected at random, and counts the number of times a node is visited, and this turns out to be betweens. The first thing to note, first of all, that in terms of what happens in most networks, these regimes are really unrealistic. It doesn't actually happen like this. Yeah, flows don't go along geodesics because you have to know an awful lot about the network to be able to make the flow go along geodesics. It requires the knowledge of the whole network and assumes there's a target. I mean, it just doesn't happen that way. We've just seen there changes in outcome, changes the count, gave me very different centrality scores. One was got betweenness, and got closeness. To the same regime. It didn't change anything. And further simulations on real data show the centrality measures perform very poorly if the wrong regime is used. Very poorly because we know outcomes. He did it on the Florentine boundaries where we know about the Medici's and how successful they were, etc. So what really this shows is, first of all, that the kind of assumptions we make about the centrality routines, yeah, unless you really think deeply about what is going on, they produce often the wrong answers. So perhaps we should do the whole thing by simulation. Computers are pretty powerful now. Perhaps I should see what regime I think the flow is going to go through the network, put in my network, run some kind of agent-based model and use that to get my centrality score. Okay, so far I've given you three particular perspectives on cell trait. I'm going to come back to those in a little while. But for everything I've done so far, these have been undirected binary data on a connected network. And can we extend these perspectives to more complicated data? The answer is some very easily and some a lot more with great difficulty, if at all. The induced perspective, the second one, requires no modification at all, except obviously whatever that graph invariant is, that thing I'm going to capture the whole, it's got to work on the type of data we've got, that comes without saying, but that's fine, yeah. For the walk, yeah, and flow thing, disconnection and values are an issue, but direction is easily accounted. Yeah, but I might start the flow through disconnected, well, there isn't a flow. So, and we kind of do some tricks to get around that, kind of connections or values for that flow that are very large. So, undirected, disconnected binary data. Yeah. Walks are not defined between components, so we could use only walks that do exist. In other words, we do things within the component. That's a very common way to do that. But this may distort things. As a component of a dyad, each node has maximum closeness centrality. Yeah, it's only got two people in it, but I'm connected to everybody else in my component. Whereas it could be a lot larger component, which has maybe just one or two edges missing, and yet those people get far less closeness, which doesn't seem right. So there's a distortion effect that we need to take account of. As I said before, one way around this is to assign large values to impossible walk rates. And important is that there's a real issue with undirected, disconnected, binary data for eigenvector centrality, which I do want to just briefly talk about. This is something which is more recent. People make some suggestions. First of all, treat each component separately. Yeah. Well, that's actually not a good idea in one sense, because eigenvector has got this odd thing that any multiple of an eigenvector centrality is an eigenvector centrality. So what this means is if I treat each component separately, I've got to work out which eigenvector do I really pick. And the trouble is, if 10 times one eigenvector is equally eigenvector as 5 times, then I may get some distortion in my network. Perhaps we should connect it by adding some edges. People have proposed that. In fact, Steve and I put this in an article. But this is very sensitive to the selection of the values that you put in. Yeah. And you can distort the whole thing again by not knowing what values to pick, and it's not obvious what values to pick. Somebody suggested, oh, it's easy, you just use page rank. But we know page rank is a centrality measure. It's a thing that's used a lot in computer science. But you don't notice that actually page rank does a normalization right at the beginning. So in fact, it does still have the distortion. I do have an alternative proposal. And that's called, I first of all called it normalization, but somebody told me that's not normalization, because normalization is when you're trying to compare what happens in the network where somebody's got the alternative to be connected to everybody else. So I've changed the word to regularization. So regularization removes the distortion from separate components. And this is one possible, I'm not going to explain that. This is one possible way of doing it. I'm just going to show it to you on a network. Here's a network of 4 isolates. Here's a network got 2 components, and I want to work out the eigenvector centrality of people in those 2 components. If I put this into a standard eigenvector centrality routine as a whole network, what would happen is these people all in here would get a score, and everyone in here would get 0. Now that would seem a bit rough, that Sylvia, who seems to be quite well connected in here, would get a lower score than Ruth, who doesn't seem to be in the best of positions. So this is what we're trying to get over. I could run eigenvector on here and eigenvector on here, but how do I compare the scores from this one to this one? That's what that formula tries to do. So I apply that formula, and this is the one here. I put down the degrees so you can see. Let's just go back and remind ourselves of a couple of things here. Well, Vern and Ruth, I would expect Vern to get a lower score than Ruth, because Ruth is connected to somebody that's well connected to everybody else, and that's what eigenvectors meant to do. So if I come back to one here, Ruth, we see has got 5.82, Vern has got a score on the top of 4.12, so yes, big tick, managed to do that. Equally well, I might want to put one component in red and one component in blue. The bigger component is in blue, so I would expect, for example, Laura, who's in the bigger component connected to 5 people, to do a lot better than Sylvia in the small one. She's got 12.54. But equally well, I want somebody in that smaller component to do better than somebody in the bigger component. And we can see that happens. For example, we can see that again, let's not take that. We could take Catherine, and Catherine does better than Ruth. So I know Catherine's connected to 3 people, Ruth's connected to 1, but it does look as if these things are comparable, and we could do tons of other studies to say, yeah, this works pretty well. I'm not saying it's perfect, but I've got problems justifying the formula that I showed you in the previous slide. Okay, other thing we could look at is directed data. What do we do with directed data? Medial methods like betweenness all work fine in directed data. Yeah, no problem, you don't have to do anything. Yeah, every one of those medial methods, because of how they work, is fine. Most radial methods, of course, use in and out versions. We're used to that with degree. Yes, it's in degree and it's out degree. That's fine. For cats, the Hubbles, you know about those measures. Then basically, for directed data, you work out on A and you work out on A transpose. One gives you the in version, one gives you the out version. But do note, eigenvector has some issues on directed valued data. It doesn't really work in essence. It does work in some cases, but lots of cases it doesn't work. It just gives very odd looking answers. And I would always tell my students, don't do it. The way around that is to use the eigenvector of AA transpose and A transpose A, and that's known as the hubs of authorities. And more recently, some work I've done with David Scotch, we said, well, why don't we do this kind of thing on the Hubble and the CATS methods? And these are the formula that we come up with to actually do that. In essence, what this really says is, look, you can deal with directed binary data. Value data, okay? What are the values? Well, you've got to take account of what the values represent. Do they represent similarities, such as frequencies, probabilities, strength, etc., or dissimilarities, cost, distance, travel time, etc. So you must take that out into account, but it's easy to convert from similarity to dissimilarity data. So in essence, that's a bit of a red herring. Degree, you take the sums or the average. Eigenvector, CATS, etc. has no problems at all. The shortest path type measures, we can define optimal paths, but this can be compensatorily very demanding. Yeah. One of the best things to do is to dichotomize at different levels. Very simple, you can get around for ages. It works really well, and I would recommend doing that. And if you've got categorical data, you create separate, obviously, networks for each category. I think that's by far the best way of dealing with that kind of data. Okay, near the end. Negative ties. Degree's fine, but you need to reinterpret it. The walk perspective really doesn't work. Yeah, things don't travel through things in that kind of way. I mean, it just doesn't seem to work. And data often has a mixture of positive and negative ties. So one thing we've proposed is something called PN centrality, which mixes positive and negative. The way it takes care of negative ties is to think like this. It's not really good if you're disliked by someone that's got a lot of positive connections. There's somebody that's really central positively in the network and they don't like you, that's not very good. But if everybody dislikes the person that dislikes you, then that's fine, because nobody takes their opinions of any sense. And this again is a formula that we've got that helps us do this with the positive ties and the negative ties. There's good mathematical reasons to do this. What comes out is that negative ties seem to have twice the effect on your centrality as the positive ties. So don't make too many enemies. How about multi-mode? Well, I'm just going to look at two-mode data here. There's what's called the dual projection method, which a lot of people do, and I saw some today. Yes, you look at both A transpose and A transpose A. That's no good if you've got more than two modes. But what happens is these things here are both symmetric and valued, and there's many, many techniques that work really well on symmetric valued data. The dual projection method says calculate both these, but recombine them in some way so that you take account of both parts of what's going on. Really going back to Freyger's original thing about the duality of the two ways of doing this. Or use the direct method. Yeah, the direct method, what you do is you don't project your network. You keep it as a two-mode network. You do the calculations, the centrality, as you would normally do. Yeah, but you only do only one or two things you've got to worry about. First of all, if you just want to get a rank order of who's the most central and who's the least, that's fine. You didn't do anything. Don't mix up one mode with the other. Yeah, keep the modes separate. If you want to compare those two networks, two-mode networks, then you've got to recognize the multi-mode nature and you have to normalize these in a different way. And formula all there for doing this. It's a very easy thing to do. There's tons of work's been doing that. The induced perspective works fine in our multimode data. Walk structure has some problems with the direction axis with direction. Yeah, the walk structure perspective. You've got two-mode data. Agencies usually with one mode. Yes, people go to events. Events then go to people. Yeah. Authors write journals, journals don't write authors. So there's always some direction in there. Again, the flow perspective makes that a real issue because things don't flow in that way, but the agency isn't in the right area. So, in summary, the walk perspective gives a classification and is agnostic about the application. Yes, it doesn't actually take any account of what your application is. Yeah, that's entirely about the structure. It is a total structural approach. The induced perspective allows us to use methods relevant to the application. Yes, I can come up with these graph invariants which are dictated by my research questions, by my data, by what I want to know. So that they are no longer agnostic about the application area. You should be able to think about the area of application. And the flow method forces you to think about the application. Yeah. So in essence, these go from agnostic to you should have a look at it, to you must have a look at it. All perspectives require us to be aware of the type of data we have, what mechanisms we're trying to model. And I think that was the message. I'm trying to show you that these perspectives all have mechanisms associated with them, and those produce very different results, and can produce very different results. And we really have got to be very clear about what's going on. I see too many papers that all they do is they run between this eigenvector closeness, degree centrality, and say, look, we've run all these centrality measures, this person's the most central, without thinking at all about what that really means for their data. And that's what's crucial, and understanding and using centrality properly. And please, please, please do not invent a new centrality. Thank you. If you want to read this, it's in here. I think it's any questions time. Steve will answer as he's still there. Yeah.
Thank you very much. So my question is more related to leak detection. I know you, yeah, it's not entirely, but I'm seizing the opportunity that you're here. And I know you've written about community detection. Okay, so how in signed networks, how do you think conceptually of negative links versus non-existing links? Yeah, how do you think about that conceptually?
Well, of course, everybody immediate answer they go to is balance theory and saying, you know, what I want is positive links, but particularly generalized balance, which takes more account of this. I want positive links within the community, negative links between the community, and if there's non-existent links, that doesn't matter because it's the positive within and the negative between. The problem with balance theory and that approach overall is that there was always this idea that things would fall into some kind of balance, well, not just balance, but clusterable, which is the more generalization of that. That's how the data would fall out, and actually over time, it would fall into that kind of category. But the answer is all the evidence is that it doesn't. I think one of the issues with negative ties is we're not very good at thinking about negative ties. We're looking at it too structurally, and I think that's the problem with the community detection. That if you're collecting data and you ask somebody, you know, all the time, there's periods of time when they don't like somebody, then they do like somebody, then they don't like somebody, that it's unusual for there to be a strong negative tie that exists over a longer period of time. And I think that's the problem with that balance idea. Personally, if I had that kind of data, I think I would cluster it just on the positive ties and then see where the negative ties lie. And actually say, well, okay, can I get some kind of interpretation from that? I really wouldn't worry about non-existent ties. Again, it depends whether those non-existent ties are positively non-existent. Is that because somebody says, well, I don't really want to have a tie with that, but I don't dislike them, but I don't want to? Or is it structurally like that because I just didn't even know they were there? But I think it's an issue that people are beginning to grapple with more and more. But I'm not seeing anything particularly stronger about than the standard clusterability things. But it's about thinking about the data. It's a lot easier. I mean, a lot of people do it on voting data. I mean, I've seen all this stuff on, whether you vote the same way as something in the party, or you're opposing them for a particular bill, or you don't vote. That's very good because you get positive, I vote for it. Negative, I vote against it, or I can abstain. Those techniques, those clustering techniques, work quite well for that. But other kinds of negative data, I don't like the statement there's such a thing as negative tie data. There's very, very different types of negative tie data. And I think your community section is doing that. We need to take account of what does that negative tie really mean? What does it mean for the individuals in there? How come you've coded it as a negative tie? I'd be more interested in looking at the centrality scores and things like this, and maybe clustering on other techniques rather than just going straight to the network as it stands. Francisca.
Thank you for that, Martin. I really enjoy the perspective of the answer for this.
Right.
So I was wondering about the issue of, because you mentioned directed ties, but I was wondering about reciprocate ties. What happened with that issue? Because I think that's also very difficult.
Well, I think, that in centrality, that's not, I mean, if it's directed, then the fact they're reciprocated contributes to centrality to both sides. There's no difficulty, I see, in reciprocated ties. I think that maybe one area where it is a bit more interesting is where the tie cannot be reciprocated. And that's, I mean, classic things would be kinship networks, mother-child. I know biology's gone a long way, but it hasn't gone that far yet. But there's other, I mean, I've also been asked to think about directed two-mode data. I'm thinking, where does that exist? One obvious place it exists is probably on dating websites. Heterosexual dating websites, because, is it the man that asks the woman out or the woman that asks the man out? So who does it first? But it's going to be first, so it can't be reciprocated unless by chance they both ask at the same time. And I've been wondering to what extent our measures and things can capture things like that. But generally speaking, reciprocation, is something in terms of centrality that just the directed version takes care of that. It's a bit warm in here. I'm not surprised there's not many questions. Yeah.
I worked time with networks that relate to both reagents, don't want. They try to hide their links.
Right.
So how can you measure that hidden? It's like with, I don't know, the approach I took was trying to predict those links with measures like used for missing links or link predictions.
Yeah.
What do you do?
Yeah, well, maybe, link prediction would be one obvious way of trying to do that. The problem is if people really are trying to hide those links, then I mean, the best way is to turn off the idea that I'm going to do just a quantitative, my network is given, but go back to qualitative things. And if you can interview people, ask them who are the most central people there are in the network, because they'll know, even though that you might not be able to get to that individual, that person is trying to hide their links, but other people tend to actually know who those people are. So that's one way of doing it. So I think that's more of a data collection issue. I think for predicting centrality, then some of those centrality measures are particularly sensitive to missing links. but certainly betweenness is particularly, but whereas something like degree is not, because it's a local measure. So you would tend to get a reasonable idea from that. If everybody behaved the same, of course, it would be fine, because you really want to rank order, but they don't. So that's not. So there's not an easy answer to that question. It's just data collection using many techniques as you possibly can to try and find out about the missing information. And I say usually other people know, and they often don't. Yes, Alejandro.
I have two questions. The first one is related with the multi-level networks.
Right.
Because in principle, it's very hard to make any difference with multi-level network. In a sense, if you just look at the structure, it is basically a network with attributes.
Yeah.
Right? So I was wondering whether you can just say there if you have thought about multi-level network or how you can treat some of these ideas that you have there over there.
Sure. Well, again, I think going back to some of those perspectives, you could look. I mean, there's certainly you could look at the induced measures and you turn around and say, well, those are going to work perfectly. I mean, the problem with multi-level networks again is what's going on there. And if you look at the flow idea, then you've got the real complication of is it stuff flowing in this level, or has it get from this level to that level? Then is it flowing through that level? Is it coming back down again? And I think that's a level of complication that requires an awful lot of thought. And it may be that your first thing to do is to separate out the levels and run some centrality within the levels, and then start looking at centralities between the levels to see what changes the multi-level structure actually has on that network. But I don't think there's any easy answers to that question. And it's I mean, a lot of people are doing a lot of multi-level networks now. And I haven't seen anything that I look at and I say, oh yeah, that's the way to do it. I don't think anybody's come up with any good way of doing that at the moment.
In my second question, if I
There's another question. Is that a question? You know how long he goes on for when he starts.
No, but well, so I was thinking about this is now discussion between bibliometricians and network research. In terms of for them, for example, citation, they use a lot of linearities, cosines, things like that. And some of them claim that some of the things that social network research are doing, which care more about the structures, doesn't really apply that well in the context of bibliometric. And some of the reasons, because, for example, citation, I can still use citation, but I don't need the flow. And I was wondering, do you think it might be a hidden problem of like the question that you made before, or do you think there is maybe something that we haven't learned that well?
Yeah, I think citation data is quite. I mean, there's very much a bandwagon effect, obviously, in a lot of citation work. So, to what extent that is actually happening? I mean, the whole of science is full of amazing discoveries that have not actually been, have not come to light until after the poor person that did it died. Or somebody's become very famous for doing something they found, well, somebody else did it 50 years earlier and their work has not been cited. So I think that there's a lot of problems with the structure of citation data and where we get it from. I think that's exacerbated even more by the whole online nature of how we actually now get citation information. And I worry about biases occurring there. I mean, it's a lot of work to clean the data these days. A lot of it is pretty shoddy when you actually look at it. And then you've got the added complication, of course, people don't cite things properly. That happens quite a lot as well. Right, but then your question was about the various indexes they use and whether, I mean, it's like all these things. I think both approaches are perfectly justified. And I think I always say about network analysis, it's not the answer. It's one of the pieces in the puzzle. Let's say, look at the rest of the puzzle. You're not going to solve anything by network analysis, but it will help you get closer to a solution, help you to understand something deeper that you might have missed if you didn't use network analysis. But please use other methods. It's not an answer at all. Yeah.
Okay, now I'm ready. I have a question that's more related to like the community of researchers that do network analysis.
Yeah.
Because I think it's pretty clear that we can work on many, in trying to find some indicators and trying to understand how variables interact with themselves, but sometimes the answer lies on actually asking the humans that are involved in the networks how things work with each other to understand some kind of structural, or the structures in which they are. But I was wondering also, like an early career researcher, I'm trying to get into this area, which also implies publishing at some point. And I was wondering how well received is to do mixed methods of political studies on social networks within the area. I don't know, because in some disciplines, it's like there's a very clear divide. I'm
Right.
not sure how it works.
Yeah, well, it depends on which journal you're actually looking at, but I think if you looked at the journal Social Networks, then there are quite a few qualitative papers that have been accepted in there. The answer is that there's only quite a few, because actually not many get submitted, in all honesty. Now, I was the editor of that journal for 12 years, I think. And, you know, I was very encouraged when I got a very good qualitative analysis.
Just so I can further on this, what is a good
Well, basically, well, first of all, what is a good qualitative analysis? Usually, most of them are people that are analysing some kind of textual or other data using network methods. So they've collected the data itself is completely, usually interview data, obviously, but there could be other kinds of data. People take photographs and things like this. But then what they then do with that is they take that information and in some way construct some kind of network from it and then analyse that network. And that would make it very good for the Journal of Social Networks. I said innovative ways of collecting that data would be, and actually innovative ways of collecting data we would also think was good. I mean, I can think of one or two people that collected things that were in quite an innovative different way. But yeah, just the standard semi-structured interviews. I don't know. In terms of using network techniques to analyze that in some kind of imaginative and different way, it can't be just completely standard for social networks. I mean, what's happened over the time? I mean, I've been doing social. I'm going to admit this now. Probably the first time I started doing social network analysis was in 1977. Before a lot of people here were born, not everybody. But at that time, the only journal that would take a social networks paper really was the Journal of Social Networks, unless it was incredibly, American Journal of Sociology occasionally took one or two, but they were hard to publish. I mean, you got Mark Granovetter's paper, The Strength of Weak Ties, the most cited paper in sociology. It was rejected, but Danny sent it in. Very famous rejection. But then social networks. But nowadays, you will get social networks applied across many different disciplines, and many journals would now take it, and it's an accepted method. When I started, it was not an accepted method, and most people would just say, "Well, what is this? I don't know what this is. Don't try and publish it here." But now it's accepted. So I think you can, in terms of qualitative work, if you're using network techniques, you needn't publish it in a networks journal. Qualitative journals will take those. I mean, I've had journals in cultural sociology, which I would not say is particularly quantitative journal, but that's about again, a lot of that as well for those kinds of things is getting good network visualizations, which you can then talk about. I mean, I wouldn't send an ERGM to qualitative, to cultural sociology. They wouldn't accept it. So it's thinking about who's reading the journal. And again, as an editor of journal, I saw some really good, highly mathematical papers. Now, I'm a trained mathematician, so I knew it, and I just said, I can't publish this in here. These people would not understand a single word of it. Go and publish it in this journal, that's where the readers of that journal are. And you'd be amazed at how many journals, how many papers they got in which they didn't cite a single article that was in a recognized network journal. They didn't have to do social networks, they could have done network science, connections, social structure, but there wasn't. All they were articles in IEEE journals and physics journals. Yeah, they don't get through. There's one more question. We can finish. Oh, two more questions. Yeah.
I want to go back to the idea of the indirect centrality because for me that is something I think and also I wanted to ask you what kind of fields or like topics they work with this kind of centrality. Because for me it's more like the idea of emerging properties in complex systems. I think that you work like really well, and also like the stability of systems, like when you are making some perturbation to some data of, for example, a network.
Yeah.
How much the importance of this law
Yeah.
in the final.
Well, I think for the total centrality, indirect centrality, a lot of that would be about well, in the area of business. So if you're going to do a restructuring, and then you're moving somebody out who is going to destroy the centrality of a whole load of people, or perhaps you want to move somebody out because they're taking a load of centrality away from some people. So those kind of organizational networks is one particular area. That's the first one that comes to mind. And your examples, but
No, also for me it was like when you are, I don't know, studying like a lattice.
right,
A lattice with oscillators and things like that, and you make a perturbation in an oscillator,
yeah,
then you can see like phase transitions and things like that. That also you can measure what is the importance of this oscillator in.
yeah,
And I think that is kind of centrality that also.
yeah. Yes, yeah. But I think a lot of the ones that I'm doing there, it's all about disrupting and changing the network or interventions. That's the other reason a lot of people want centrality is because there's some kind of intervention. So areas of public health, for example, they want to identify who are the individuals in there. If I've got to make some change, who are the people I've got to influence? Because and that's back to that one when I said about the key player problem. I kind of just mentioned it very briefly, but that's kind of related to those kind of areas. So it's about changing networks, I would actually say.
I think we can continue the conversation in the social gathering.
Sounds nice.
So,
Sounds
finally grab a beer after 2 days of work. But before we move there, I just wanted to.
Oh, thank you so much.
Thank you.
Nice to see you again. Something very close to my heart because it's a nice bottle of Carmenere that has my name on the top as well. Thank you so much. Thank you.